Okay, so let's finish up the Intro to Forensic Science PowerPoint by covering some additional scientists that have made contributions. So once again, I'm just letting you know when these people live. You do not have to memorize dates for a quiz or an exam. Okay, so Matthew Orfia is considered the father of forensic toxicology. His work was very important. I would not have liked to have worked for him because what he basically did was poison, kitties and bunnies, and then he would dissect them and see what organs were affected. So he's the reason why we know, what cyanide does and what carbon monoxide does, and all these different poisons. And he actually developed a bunch of isolation techniques, which are still used today. Francis Galton is considered the father of fingerprint analysis. And he is the one who determined that fingerprints basically, do not change over a person's lifetime. He discovered the three main categories of fingerprints, which are arches, whorls, and loops. And he also developed a method still in use today for individualizing fingerprints. Now, obviously, things have changed. We now have new development techniques like using fingerprint powders and super glue, and we can digitize a lot of that evidence. So we now have a fingerprint database, but the basic principles remain unchanged from when he wrote his original text in 1892. And in terms of science, that's amazing for those principles to hold true for, that long. Carl Landsteiner is considered the father of forensic serology and also the father of DNA analysis. So he was the first one to discover, we have different blood types. Okay. Prior to that, doctors just thought, well, if we're all human and we all have blood, it must be the same. And sometimes when they gave a transfusion, it worked great. And other times the person developed blood clots and died. And Landsteiner was the first one to figure out that, people are different blood group types. So if you're type A, you can't receive a transfusion from someone who has type B blood because it's going to react and cause blood clots. So he was the first person to discover that. And from that, serology was developed. And from serology, DNA analysis was developed. Okay, Calvin Goddard is considered the father of firearms analysis or ballistics. So he was the one that figured out that, every firearm is basically different and individualizing because of manufacturing marks that are on it. And those marks are then imparted onto the bullet and the cartridge case as that bullet leaves the gun. He also developed something that is used in trace microscopy and a lot of different disciplines, which is the comparison microscope, which is basically two microscopes hooked together. And so you can put a sample from the crime scene or the evidence here, and then a known sample here. So let me show you an example of this. Okay, so these are samples that were taken from a commercial burglary. So basically someone broke into, like a Target or a Walmart, and to pry open the door, they used a big crowbar. So this is an example of tool marks. So these are marks left by the crowbar on the door jamb at the business, the Target or the Walmart. And then when a suspect was developed, they found in the possession of that suspect a pry bar or a crowbar. And so they brought that into the lab and then used it on an identical door jamb. Okay. And then lined them up on the comparison microscope, and you can see these scratches are what we call striations. So these are things that you will also see on bullets and cartridge cases. But here you can see those striations from the evidence line up perfectly with the striations produced from the suspect's crowbar. So that is considered a match, and it's okay, sir, now you have some explaining to do because your crowbar was the one that was used in this commercial burglary. here's an example of the striations on the firing pin of a bullet. Okay, so basically this is where the gunpowder is, and then when it ignites, the bullet shoots out of the gun. This is from the bullet recovered from the victim at autopsy, and this is a bullet that was fired from the suspect's weapon in the crime lab. And once again, look right here. Okay, you can see that the striations line up. So this is an example of pattern evidence, as was the previous slide, but this would be a match. So this bullet was fired from that gun. Okay, so that's an example of pattern evidence and a match, and that also is on the comparison microscope. Okay, so here is the guy, and we're almost done. This is a guy who is considered the biggest dog in forensic science, hands down. Okay, Edmond Locard. And Edmond Locard was a triple threat. So he went to medical school. I mean, talk about an overachiever. Then he went to law school, and then he also became a police officer. And he was working for the police in Lyon, France. And he was the first person to say, you know, go to his supervising officer and say, you know what? I think we should use science to look at things that we collect either from suspects or from crime scenes. Okay, and obviously at that time in 1910, we're not talking about big fancy, you know, DNA machines or chemistry machines. It was basically, here's a basic microscope. Let's look at things, you know, if there were, you know, how, if we heat something up, at what point does it melt? That would be another example of an observation. Or let's put it in acid. Does it dissolve? I mean, we're talking very basic scientific things that they could measure. But he was the first person to think about how evidence could be transferred. And so he came up with the single most important principle in forensic science, which is Locard's exchange principle. Okay, or sometimes it's called Locard's principle of evidence exchange, or LPEE. So here is the wordy definition. Whenever two objects come into contact with one another, there is going to be an exchange of materials between them. Or kind of the dramatic way to say it is every contact leaves a trace. Okay, so this is why now when you see modern crime scenes being processed, the technicians are wearing those Tyvek suits. Basically makes them look like little Oompa Loompas, like from Willy Wonka, but it's because they don't want to leave a trace of themselves behind. You know, back in the 70s, if you look at historical photos, you'll see detectives smoking cigarettes, you know, at a homicide scene and eating a sandwich. You know, that can't happen anymore because even a drop of perspiration can leave enough DNA to be detected. You know, we have something now called touch DNA, where it's literally, you just have to touch something once and that DNA can be detected. So, in other words, a person who enters a crime scene is always going to leave something behind and is always going to take something with them. It's always going to happen. Now, can we always detect it? Nope. Okay, so the exchange of materials always happens. Yep, even if it's on a molecular level. Okay, think of like hugging a friend. Okay, if you hug a friend, you're probably going to shed a couple of hairs from your head onto that person, maybe some fibers from the shirt that you're wearing. You know, if you guys are both, you know, sweating a little bit, you can transfer, you know, maybe some dead skin flakes or perspiration. Even that minor hug is you're going to transfer materials. Now, can that contact always be detected by the forensic science lab techniques that we have today in reality? No, it can't. Okay, on TV, yes. And I want you to pay attention to this. The next time you watch a crime-related show, you'll notice that they always find DNA. Always. Okay, they always find a fingerprint. There's always something on TV because that makes it exciting. Okay, in reality, no. So for example, let's say we have a big pool of blood, okay, from a victim who was stabbed, and then the offender let's say, cut him or herself while they were stabbing the victim, and they dropped just a drop of their blood into that huge pool of blood from the victim. On TV, absolutely, they would be able to find that offender's blood. In reality, no, because DNA techniques, the way they are now, can only pick up a mixture of two people if it's in a ratio of less than 10 to 1. Okay, so a big pool of blood with a little drop in it from someone else, that could be 10,000 to 1. You will not pick up that minor contributor. They're there, okay? We know they're there, but modern techniques are not going to be able to pick it up in reality. So I think that's disappointing for a lot of even new forensic scientists who are going into the field. You know, they want it to be like TV. They want to help the case. And unfortunately, it doesn't work that way. So, you know, the science behind it, it makes sense, but on TV, they always get that lucky break, and they have the most amazing equipment, and it always works that they pick up, you know, a single hair out of a sewer or something. It's just not realistic. Okay. But the exchange always happens when two things touch each other, even if it's on a molecular level. Okay. So definitely know who Edmund Locard is and understand what this principle is. And that's the end. Okay. Thanks, guys.